So, welcome to this course in radiation damaging materials, or actually the net lectures of it. So this is a series of slides for which I've also recorded the speech of the slides, and it will be part of all the materials of the course. So what this course is dealing about is, as the title says, is radiation effects and the materials. That is how ionizing radiation can damage materials. And what all of this means and what all the kinds of damage are, what kind of materials are considered is something which will be clear, obviously, during the course. And as a little bit of background, why I'm doing this is that I have been working this exactly this field for 25 years, and I published more than 400 scientific publications on this topic. So I have a fair deal of knowledge of this, and of course I've also used not only my own knowledge but literature as sources. So what are really the aims of the course? Well, of course the main aim is to understand what radiation damage is, what it really means, and how it's created. And this is actually one big part of the course, is to give the latest scientific understanding of the mechanism by which radiation damage is created in materials. And then what this leads to, not only the primary damage production, but also what the eventual outcomes of this are. And we will see that these outcomes can be quite interesting, and sometimes actually and many times beneficial and not only harmful. When people hear the word damage, they often think of harmful effects, but in fact there are many useful effects as well. And you will see towards the end of the course that, for instance, you can do cute things like changing the color of flowers by using radiation effects. This may be not so obvious, but it actually works and has been done, and this will come up later during the course how that happens. In connection to this, we describe both the theory and experiments, but also quite importantly modern computer simulations which are used to model radiation effects. So what do you need to do to be able to absorb this material? Well, this is a physics course. Depending on country and system you are in, this will be to the third, fourth, or fifth year physics university students. So we assume a good deal of pre-knowledge. Basically, in addition to the basic physics, like first year courses, one should know the basic of thermodynamics and statistical physics, and the basics of quantum mechanics. We don't go very deep into quantum mechanics, but we understand that we assume that people understand the basic quantum mechanical nature of materials, and similarly the basics of chemistry. And also, very importantly, we assume people have basic knowledge of materials physics, that is atomic structure of matter, crystals, the amorphous state, and so on. And this material, it consists of the lecture notes, which are already available in the web. They have been for several years, and these videos, and there will be additional material also. And the knowledge on this course is, much of it is my own knowledge and the other visiting lecturers, in addition, a fairly good deal has come from this book, the book by Gary Wass, which is quite an extensive book on fundamental of radiation materials science. It fairly much focuses on metals, which is also the best understood part of this, but many of the parts are relevant to other materials as well. And in addition, there are a couple of review articles which are useful and used as background for some of these. And these review articles are available on the course webpage. So to get to the business, well, first of all, to understand what radiation damage is, we have to understand what radiation is. And by the way, here you note that this course is given at the University of Helsinki. So this is why the terminology, new terms are generally always given in bold font. But then in blue italic font, there is a translation to Swedish and Finnish of the same term. So this is something, if you don't know Finnish or Swedish, you don't need to worry about this. They are just the same word given in different languages. Well, the word radiation in all these three languages, which are the three languages I know fluently, it has a quite general meaning, because of course people talk about radiation, solar radiation or solar, the sun shines, it's a kind of radiation and so on. And more scientifically, in electrodynamics, Maxwell's equations of motion, which are the basis of classical electrodynamics, they say that any moving charge particle induces an electromagnetic field, but if the charged particle is also accelerated, that is, the velocity is increasing, it will lead to a propagating electromagnetic field, which is electromagnetic radiation. A simple example of this is radio waves, but it can be also other kind of waves. For instance, in the synchrotrons around the world, very high energy electrons are bent in the synchrotron, and this bending causes it's a kind of acceleration, and this acceleration causes them to emit actually X-ray radiation. In principle, by this decelerating or accelerating charged particles, one can produce all kinds of electromagnetic radiation. But then there are, of course, other kinds of radiation. One is radioactive decay, which is sort of the standard way of the standard description of dangerous radiation. Then there is the sun, the stars, the headlights of our cars cause radiation, and so on. But not all of this kind of radiation is harmful. Like basic radio waves, they are all around us and are not harmful in any way. So for this course, when we talk about radiation, almost without exception, we mean what's known as ionizing radiation. And the definition of ionizing radiation is, well, to put it shortly, it is that it's radiation which can damage materials or humans or something. Of course, the basic meaning of the original meaning of the verse is that it causes ionization, that is, it ionizes electrons from a ground state into an excited state. But it turns out that some kinds of so-called ionizing damage radiation don't necessarily, the damages may not be caused by ionization. So also this is a bit misleading. But this is also a point where the terminology starts getting a bit confusing. First of all, ionizing radiation is a legal term. It's all countries I'm aware of have radiation protection laws which discuss ionizing radiation and what are the allowed doses for it and so on. We'll return to this in a moment. But then the other thing which can be confusing is that we physicists often forget to say this word ionization and talk about radiation as when we mean in the reality ionizing radiation. On the other hand, the common public, again, many of them have the picture that any kind of radiation is harmful, which of course is not true. I mean, radio waves are not harmful, and in fact, any kind of radiation, if the dose is low enough, it's not dangerous to humans in any way, because we are completely surrounded by different kinds of radiation, and there is radiation events occurring every second in our bodies, but this doesn't mean that we would die out of it. The reason to this is that biological processes are built to withstand the natural radiation and natural radiation levels, and that's why low doses of radiation are not harmful by themselves. So one has to be a bit careful about this, and sometimes, especially written words, of course, precise about what kind of radiation one means. Well, the reason this term ionizing radiation is used and is a fairly good term is that it's fairly well defined what it means. And this comes from basic chemistry. The strength of chemical bonds is order 2 to 5 eV, and then there is a kind of radiation that has an energy high enough to excite electrons which form the chemical bonds, and then we break the chemical bond, then this can likely lead to damage in the materials. You break chemical bonds, the chemistry changes, and this is probably not a good effect, and it can very well be a permanent effect. So this means, roughly speaking, that if the particle energy is more than 5 eV, it may be ionizing. Although, as we shall see later on in the course, this is a simplification. Strictly speaking, it's not the particle energy which determines it, but whether the particle can give the electrons this energy of 5 eV. But this is not also an exact limit, and depends on the case. And actually, in many cases, we don't fully know this. Describing this basic ionization process from really physics first principle viewpoint is very difficult, and in most cases hasn't been achieved yet. So this means, for instance, that laser irradiation, if the intensity is low, it's not ionizing, even though the photon energies may be 4 or 5 eV. On the other hand, laser irradiation, of course, can damage material if the intensity is high enough, but then it's not an ionization mechanism directly. It's a high intensity effect, which basically excites a lot of electrons by a little, but this is enough to make heat the material and then make it explode. Well, about the law, since we are in Finland, this is the Finnish law, or actually this is the translation of the Finnish law made by the Radiation Protection Agency, so this is quite a, the web link here gives a really reliable translation of the law. I want to go through this because this is not a course in the radiation legislation. We have a separate course in radiation safety which deals with the legislation. But I'll just show you that there are legal definitions from this, and it makes the distinction between natural radiation and not natural radiation. But also this is already a bit dangerous. The law says that ultraviolet radiation is non-ionizing, which is sometimes true but not always true. It depends on the energy and the condition. And here is the Swedish and Finnish versions of the law. But what we'll do in this first course package is go through what kind of particles can cause irradiation. And the first one, which I already mentioned, is photons. That is the quanta of electromagnetism. And these are, of course, very, very crucial in all kinds of physics. And just as a reminder, this you definitely have had during some of your previous physics courses. Here is a picture of the electromagnetic spectrum. So starting from radio waves, one goes on to microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. This is a simple schematic. The reality is more complicated than this. For instance, microwave and radio overlap, and X-ray and gamma regions overlap. The definition here between X-ray and gamma is fairly clear. X-rays are made by X-ray tubes or synchrotrons or something. The gamma rays come from nuclear processes, and it turns out that the lowest energy photons produced by nuclear processes can be well below the highest energy X-rays produced by X-ray processes, and because of this, these two regions can overlap. A little bit similarly, radio microwave overlap, although there the definition is more historical. It's simply a matter of definition, what's called radio, what's called microwaves. But what is clear is that here, the upper ultraviolet, the X-ray and gamma ray photons are ionizing. One important additional note here is that X-rays and synchrotron radiation are two terms which are sometimes used as if they were identical, sometimes used with a distinction. The distinction is that X-ray photons are something which are made by transitions in atoms, like in a classical X-ray tube, whereas the synchrotron radiation comes from Bremsstrahlung that is slowing down of electrons in accelerators, and energy range of the synchrotrons and X-rays overlap, and that's why sometimes they are used as equivalent terms. Well, then we have electrons. Of course, all physicists know what electrons are. It's an elementary particle which is crucial for all chemistry and materials physics because that's what binds atoms together. But the electrons can also be accelerated to high energies by electromagnetic fields. And if they are accelerated to high enough energies, they become ionized radiation. And X-ray tubes are an example of this. Cathode ray tubes, which is you have a cathode and an anode, negative and positive part with an electric field in between, and you can get electrons out of the cathode by heating it up under the field, and then you can form an electron beam from them. There are, in modern research, electron microscopes are used a lot, and also there are specific electron accelerators which can go up to extremely high energies, giga-electronvolts or higher in case of particle physics experiments. And then there is actually electron beam welding, where electrons are used for welding with fairly high energies, which are can be in the ionized range. And the electron beam welding is actually an industrial process. And just to remind people, especially young people, is that still like 20, 30 years ago, everybody basically had an electron accelerator in their home. Because the old TVs, the thick bulky ones, they typically work with a 25 kilovolt electron accelerator. They formed an electron beam, which was deflected, or actually scanned over a fluorescent screen, which was the screen of the TV. And this produced, of course, the TV signal, but it also produced a little bit of X-rays. And that's why there were, in those days, lots of warnings that one shouldn't be too close to the TV for a long time, because one could get a minor radiation dose from it. The other issue was actually simpler, is that this also the air dried because of this process, and dry air is not good for your skin, so sometimes the problems were not actually radiation, but just dry air. Well, then there are neutrons. And the neutron is, of course, one of the basic particles, hadrons in physics, but it's not stable. A free neutron decays in about 11 minutes to a proton and an electron and a neutrino. But free electrons do exist. They exist within this 11-minute time scale, of course. One source is nature. The natural radioactive decay from radioactive isotopes, which are all around us, including certainly in this room. They produce neutrons, and these in turn can cause additional nuclear reaction, but also slow down and then be absorbed, or then decay into a proton and an electron and a neutrino. So neutrons are always all around us, but at low doses or low fluencies, of course. But then they can be produced by man. Of course, in nuclear fission bombs, they produce a lot of neutrons, and there is even the so-called neutron bomb, which is specifically built to produce a lot of neutrons. And obviously, this is harmful, although in case of nuclear weapons, the biggest harm is not only the neutron, but the pressure and heat wave which comes from the explosion. But one place where they are produced routinely, controllably, is nuclear fission reactors. In fission reactors, the basic idea is the chain reaction from uranium or plutonium, which is mediated by neutrons, and because it's mediated by neutrons, of course, these fission reactors have to be a strong neutron radiation environment. Initially, their energies are in the mega electronvolt range, but in regular operators, they are thermalized to sub electronvolt energies, which leads to an operation of the reactor. And then the other big source of neutrons is nuclear fusion reactors, which exist, although not on an energy-producing scale yet, but there are tens of nuclear fusion reactors operational in the world, and the biggest ones, when they are run with deuterium and tritium, produce neutrons during operation. And eventually, if a fusion power plant is ever constructed, this will produce quite a lot of neutrons inside the reactor. And of course, the counterpart in the weapon industry is the hydrogen bomb, which produces a lot of neutrons. And in this, the standard reaction, the deuterium plus tritium reaction, produces 14 MeV neutrons. And actually, for the neutrons, the kind of neutrons which are produced are classified by energy by this scale here. It's not so important for this course to know exactly remember which energy is which category, except it's good to know that these fast neutrons means high energy neutrons, which are quite damaging for materials. And then there is ion irradiation. That is, ions are, of course, by definition, charged atoms or molecules. And ions exist everywhere in any chemistry lab. We'll deal with ions in one way or the other in a chemical solution. But if you take ions out of the chemical or materials environment into a vacuum, then you can start accelerating them similar to the electrons with electromagnetic fields. And one can get them to high energies, which then lead to ionization, them being ionizing radiation. And the accelerators which are used, their energy range is quite wide. From about 10 electrovolts, which are small ion guns, they can be fist size, to extremely high energies, the current record being the Large Hadron Collider at CERN, which accelerates ions, protons, and lead ions to protons up to 7 tera electrovolts, which is a huge energy in particle physics terms. So ion accelerators are important for particle physics, but also for industry. Actually, every silicon chip which is nowadays made and has been made for decades has been made in part with ion implanters. This is not the only technique. There are many, many techniques which go into making silicon chips and the computer technology, but ion implantation is one of them, and this actually makes accelerator technology a multi-billion-dollar per year industry in the world. There are also other industrial uses, but money-wise, by far, this computer industry is the biggest one. They're also used widely for ion beam analysis and ion beam modification materials. Actually, the lab where I'm speaking is the accelerator lab at the University of Helsinki, where we are doing both ion beam analysis and ion beam modification with a range of medium size and small accelerators we have installed here. Well, ions can also be produced in radioactive decay, similar to neutrons naturally. They are not all around us because ions made in radioactive decay slow down very quickly, on very short distances. They do exist all the time, even in our body, but they don't travel far, similar to neutrons. And then what's known as the solar wind, the winds coming from the sun, it's actually mainly protons with high energies, kiloelectrons, megaelectrovolts, even gigaelectrovolts. Well, so those four were basically the most important sources of ionizing radiation. But there are many others and can be many others. One can make energetic neutral atoms with special implanters, which first accelerate ions and then neutralize them. But one can basically take any elementary particle, so one can take a muon, any charged elementary particle and accelerate it, muons, antiprotons, positrons, neutrinos, and so on and so on. There are some of these exist also in nature. The natural so-called cosmic muons are forming the uppermost atmosphere and bombarding the Earth all the time, and are a fairly significant source of so-called upset events in modern electronics. That is this radiation producing disturbance in the electronic operation of transistors in computer chips. One can also accelerate composite particles, molecules, and nanoclusters. There has even been a dust accelerator which accelerates dust particles. But the quantity for this is energy per atom usually, and not total energy, which is important. So that was a brief overview first of what kind of radiation there is. Another important question is how does this relate, connect to other fields of physics? Well, first of all, this radiation damage study is related to nuclear physics, but it's not actually entirely part of nuclear physics. This is, of course, a little bit a matter of definition, what's part of what, and sometimes people have very fruitless discussions discussing this. Sometimes it can be important when somebody defines which kind of research project belongs to some certain funding instrument, but most of the time it's just semantics, which is of course not fundamentally important. But okay, to give a bit of a view how this relates to others. Of course, radioactivity is a nuclear physics process, and this is clearly something which is part of nuclear physics. Also, neutron interactions with materials is usually considered a branch of nuclear physics. But when one deals with low energy, fairly low energy ions or electrons, that is below, roughly speaking, 100 keV, these can be used to irradiate materials. They are certainly ionizing radiation, but they don't necessarily cause any nuclear reactions. Because of this, they are usually not considered nuclear physics. Instead, when one irradiates materials with ions or electrons and modifies materials, this is considered a branch of materials physics. Or as in this title of this Gary Wass book, Radiation Materials Science, it's also a term which is, starts to be used to describe this. In any case, the final damage of materials is in any case something nuclear physicists are not interested in really, but we materials physicists are interested in. In matter of definitions, there is one more definition which has to be mentioned because it's still important and used. That is, when people found the different kinds of ionizing radiation more than 100 years ago, there's people like Marie Curie, Thomson, Rutherford, Einstein was also involved, and so on. The most famous physicists in those days were almost all involved with radiation effects in one way or the other. In the beginning, of course, people did not know what are those things which are there. Still in the 19th century, of course, the ether theory was strong. It was only Einstein and Rutherford who finally proved that the ether theory is strong and matter consists of atoms and electrons as physical particles. So they made names for the particles they observed, which were not very inventive. They were just the first Greek letters, alpha, beta, gamma, delta. And now, later on, of course, people understood them, what they are, and here is the explanation of what these are. And this is really important to know because all four terms are still used to varying extent. So an alpha particle is simply a helium nucleus, 2 protons and 2 electrons, and this is very widely used term. Beta particles are electrons. And much of the time people don't talk about beta particles anymore, but in some branches of nuclear physics, for instance, beta particles are still called that. So one has to know that. The gamma rays, that's high energy photons, or nowadays it's often gamma is used as a symbol for a photon of any energy. And this is, of course, very widely used. Any physicists have heard about gamma rays and gamma particles. And then the fourth one is delta electrons, or delta particles. And this means secondary electrons. So it's in principle, beta and delta are fundamentally the same. But when one talks about delta particles, one means secondary electrons which are produced when another energetic particle interacts with the matter. This is quite rarely used, but some branches of solid state physics still occasionally use this term delta electrons of the delta rays, although delta rays is quite misleading. But more terms which are important is the damage and dose terminology. And this is something which for this course is very, very important to know these terms and know them accurately because it's easy to also confuse these, and some people keep confusing them. So the most general term for this course is the radiation damage, which is simply defined as any damage to a material caused by any kind of radiation. And we shall see later in the course that the damage can be very small or very big, depending on case, even in a single event. But then the defects, which is a bit more specific term, this is these atoms that deviate from the order in a crystalline or amorphous material. This a defect is something which is long-lived and can, at least in principle, be observed as an atom which is in a non-perfect environment. And not all damage needs to be the kind of defects. There can be electronic excitations and so on, which are also damage, but not defects. Another distinction is really that phases. That is, ion radiation can often amorphize a material, and this amorphous material can be extremely stable. Like, say, amorphous silicon is at room temperature stable until the end of the universe if it's affected by any external disturbance. So in this case, this amorphous phase may be a perfect high-quality amorphous phase, so it's not a defect in any way, but it's still radiation damage because it's produced by radiation. And then the other point of this is that the so-called defects produced by radiation can in many cases be beneficial, have positive and good effects for the material. And then it's a bit stupid to call them damage because damage sounds negative. And in this case, it's better just to call them defects or maybe even something else, sometimes even a functional center or something like that, which makes it clearer that it's really a good thing. And more about doses. These are more specific terms and also important to know. First of all, exposure means a material which is exposed to some kind of radiation and tells that there has been an exposure, that is, the material has been subject to the radiation. And these are the measures for the amount of exposure. And these four in bold are the standard most important ones. First one is dose. It's the amount of energy deposited by radiation per mass or volume. And this is specifically the amount of energy. So the units for dose should be energy per mass or energy per volume. Well, dose rate is simple. It's just dose divided by how fast it comes. So it's the same thing, except you also divide by time. But the other term which is important is fluence. And note it's an E in the end. There is also the English word fluency with a Y in the end, but that means something different, something related to geology or hydrology. It's not a radiation term. So fluence is the correct radiation term. And this is important because many spell checker, like a standard word spell checker, does not recognize the word fluence. So you have to teach your spell checker to recognize the word fluence if you deal with this field. But anyway, so the fluence is the number of particles deposited per area or per volume. And this is really the difference between dose and fluence, is that here it's the energy in dose, and in fluence it's the amount of number of particles. And this is an important distinction to make. In many cases, it's just a trivial scaling factor. The number of ions times their energy gives the dose, obviously. So fluence times energy per particle gives the dose. But sometimes it can be very difficult to know what the correspondence is, and then it's important to distinguish the terms properly. And then there is the word flux, which is fluence per time. Again, simple once you know what fluence is. And then in radiation safety, people often don't talk about activity. This is the amount of radiation produced by a radioactive sample. And here are some units for those. The SI unit is gray, which is joules of radiation per kilogram of material. There are also many historical units for those, and I won't start going through those on this course. In physics research, it's quite common, instead of these joules per kilogram, which obviously if you deal with modern atomic level physics is not very practical, it's quite common to give the dose in units of electrovolts per atom or electrovolts per volume, which can be cubic angstroms or cubic nanometers. Then there is a special unit, displacements per atom, which is widely used in nuclear engineering and ion beam physics. And we will return later on the course to what this dPA is, and also that it's not quite as simple as it sounds about what it means. But it's still a useful scaling unit and gives often the roughly correct physical idea of how much the material has been exposed to radiation. Then if you want to think about radiation to living tissue, not only biological materials, but also materials which are alive, then there is a number of units for radiation exposure in the radiation safety, the most important of which is the so-called REM unit, radiation equivalent man. But on this course, we really won't go much into these radiation protection issues. Well, then for dose rate, obviously, you can take any of the dose units and divide by time. So the official unit is then, of course, gray per second. Then for fluence, it's particles per cubic square centimeter or square meter, or just 1 per square centimeter or 1 per meter. And then flux is the same, but also divided by time. Of course, one can use any length unit here, but these are the most commonly used ones. Okay, and as I said, the radiation protection units are many, and it's not really the topic of this course, but here is written something about them, and this equivalent dose has the important thing is that there is a scaling factor which roughly gives an idea of how sensitive biological or living tissue is for different kinds of radiation. This is this Q factor, which has different values for different kinds of radiation. This is not fundamentally very well defined. It comes more from practical experience of how sensitive living beings are to different kinds of radiation. Then there is also something known as LET, radiation energy loss per length travel, and this is almost identical term with stopping power. That is, it has units of energy per length, how fast something slows down by path length travel. And to this one we will return during the course in quite some detail what the correct and real definitions of stopping power are. That's quite crucial to understanding the nature of radiation materials. If you want a list of more of these those materials, the Wikipedia page is quite good for this. One thing one can remember that the annual lethal dose natural radiation, not lethal, average natural radiation dose in Finland is 3.7 millisieverts per year, and this is more than 3 orders of magnitude lower than the lethal dose, which is roughly 5 sieverts. So this was the first chapter of this course, so I hope I gave you an idea what the course is about, and you know some basic terminology about this. And you also know that you should not use the legislation as a sort of physics knowledge, because the legislation is done with a somewhat different purpose than physics courses and can be a bit misleading. On the other hand, it's important to know that radiation does have legislation, which of course we should follow if we do any kind of experiments with this. And then you have some basic idea of how radiation is produced, although we will certainly return to this point later on during the course. And then you know a little bit about these units, which is of course very important for any calculations in the field. Thank you for this first section.